Welcome to Dreaming Scientist Sleepy Stories tonight. We drift together into the quiet geometry of consciousness, space-time, and the deep future of our universe. A universe can slip into its ending so gently that no brightness, no motion, not even a single wandering particle remains. Only a thinning web of space-time drifting toward perfect stillness. Yet tucked inside that silence rests a strange idea that when everything reaches its final moment, the seed of another beginning may quietly take shape. Tonight, you and I drift toward the last breaths of a fading cosmos to explore why its gazores. Ending may be the first stirrings of a new dawn, a calm journey to the edge of time, where closure softens into part one of a deeper question. What truly unfolds when a universe dies? Its ending is not a sudden darkness falling across the stars. It's a slow unwinding, a long slide into a state where physics loses the ability to build or change. Scientists call this future heat death, though the words barely hint at the completeness of the transformation. To understand it, you return to something familiar, the stars. Every star is a temporary furnace, a brief creation shaped by nuclear fusion. Before fusion was understood, early physicists struggled to explain how stars could shine for billions of years. Arthur Eddington once wrote that the answer must lie in the subatomic world. He was right. Fusion of hydrogen into helium fuels the Aprilia, sun, and every star you've ever seen. But hydrogen is not eternal. The largest stars burn through it quickly, living only a few million years. The smallest red dwarfs stretch their lives far longer, glimmering softly for trillions of years far beyond the universe's current age. When the final red dwarf fades, new starlight will no longer form. This marks the beginning of what astronomers often call the stellar end era. White dwarfs and neutron stars linger, glowing faintly from leftover heat. White dwarfs cool with extraordinary slowness. Even after 10 quadrillion years, many remain warmer than the cosmic background. But cooling never stops, and eventually each one becomes a black dwarf, a cold, dense relic emitting almost nothing. Neutron stars endure even longer. Their density is so extreme that a teaspoon of their matter would weigh billions of tons. Over unimaginable spans of time, quantum effects may cause some of them to collapse into black holes. Though this depends on physics, we still don't fully understand. When the eras stretch onward, the focus shifts from stars to matter itself. Proton decay sits at the center of this mystery. We've never observed it, but many theories predict it. Giant detectors like the Kamiokande, a massive chamber of pure water deep underground, watch for the faint signals that would confirm it. After decades, no event has been recorded, yet the experiments reveal something profound. If protons decay, the half-life must be at least 10 years. As Frank Wilczek once summarized, if protons decay, then matter is not permanently stable. If protons decay, atoms eventually vanish. Molecules dissolve. Solids crumble. Chemistry itself ends. When matter fades, gravity takes over. Black holes dominate the deep future. Anything that can fall into them eventually will. The universe becomes a vast map of isolated supermassive black holes drifting through an ever-expanding emptiness. In 1974, Stephen Hawking reshaped our understanding when he discovered that black holes slowly emit energy Hawking radiation. NASA's summary is simple. Black holes evaporate. a black hole the mass of the Sun would take 10 years to vanish. The largest ones, millions or billions of solar masses, require 10 years or even more. When the final black hole evaporates, the universe enters the dark era. What remains is a thin sea of photons, neutrinos, and the lightest particles known. They drift apart as space expands around them. Collisions become rare. Eventually, expansion pulls them away from one another faster than interaction can occur. This is where the idea of time becomes delicate. Not because clocks stop, but because nothing changes in a measurable way. Sean Carroll expressed it clearly. Without free energy, time loses physical meaning. Time continues as a sequence, but with no events to distinguish one moment from the next. Yet the deepest question lies in information. In physics, information is the arrangement of matter and energy, the orientation of atoms, the direction of a photon, the structure of a star. When everything becomes evenly spread, information becomes almost impossible to encode. The black hole information paradox once suggested that information might disappear entirely. Hawking later revised that view, saying that information is preserved. But heat death raises a different puzzle. If matter decays, if every gradient vanishes, if every region looks the same, where can information remain? Quantum field theory hints that even empty space contains subtle correlations. Cosmologists debate whether those correlations can preserve information in a universe approaching stillness. No experiment yet exists to test this idea. A moment in history helps illuminate why this question matters. In 1992, NASA's COBE satellite detected tiny temperature patterns in the cosmic microwave background, variations only 30 microkelvin in size. George Smoot described the discovery with words that echoed through science. It felt like seeing the face of creation. Those patterns revealed the earliest structures ever observed. But over immense time, these patterns fade. In a heat death. Future, they fade completely. Every difference vanishes. Every contour smooths away. Heat death is not collapse. It is uniformity overtaking everything. The timescales involved stretch beyond imagination. 10 years, the last stars flicker out. 10 years, possible proton decay. 10 years, stellar black holes evaporate. 10 years, the largest black holes fade. 10 years and beyond. The universe approaches perfect sameness. Each number marks the gradual fading of structure. Yet something unexpected appears in the universe's late stages. Mass begins to lose its meaning. When every particle capable of decay finally dissolves, the cosmos is left with nothing but radiation, waves of massless particles moving at the speed of light. This is the strange territory where Roger Penrose's Conformal Cyclic Cosmology enters. Penrose suggests that in a far future where all mass disappears, the size of the universe stops mattering altogether. Without mass, there is no ruler left to measure distance. A universe stretched across trillions of kilometers and another compressed into the width of a single millimeter become identical under conformal geometry. Penrose summarizes this with a striking idea. The remote future of our universe can be conformally equivalent to the Big Bang. This raises a profound question. If a uniform, massless universe becomes truly scale-free, then what physical event marks the end of one cycle and the start of the next? Is that boundary geometric, quantum, or something stranger, something that blends both. As the universe drifts into this silent stage, a quieter picture emerges at the far end of CCC's cosmic timeline. In Penrose's view, an aeon, a complete cosmic lifetime, ends only when the universe has thinned itself almost to nothing. But what exactly is allowed to remain at that final breath? Part 2. What signals the end of an aeon in CCC? Penrose begins with a simple but revolutionary point. An aeon is not a chapter. It is an entire universe. One full existence, stretching from a Big Bang at one end to a cold, massless, scale-free future at the other, a future where geometry itself changes. Character he argues that when all mass disappears, the universe loses its ability to define scale. A galaxy spanning trillions of kilometers and a tiny quantum field oscillating across microscopic space become indistinguishable. Mass is what anchors size. Mass is what allows space-time to bend in meaningful ways. Remove mass, and the universe becomes a structure defined only by angles, not distances, a perfect setting for one aeon's end to match smoothly onto the next Big Bang. For this to work, the universe must reach a state where all mass fades away. This sounds extreme, yet it follows the natural predictions of physics across the deep future. Stars burn out as fusion stops. White dwarfs, neutron stars, and black dwarfs cool into darkness. But even these final stellar remnants are temporary. If proton decay predicted by many grand unified theories is real, then matter itself is temporary. Japan's Super Kamio Kondi detector has searched for proton decay for decades. No decay has been observed, but the absence of detection only increases the lower limit of the proton's lifetime to more than 10 years. Physicist Frank Wilczek once said, "If protons decay, then even matter is only a transient phase." Within CCC, this becomes a requirement, a necessary step toward shedding the last anchors of scale, long before protons unravel. The universe enters another era dominated by its heaviest structures, black holes. As long as they exist, the universe retains mass, curvature, and scale. But Stephen Hawking's 1974 discovery changed everything. Black holes emit radiation. They slowly evaporate. A stellar mass black hole would take around 10 years to vanish. The largest supermassive black holes, the giants at galaxy centers, need roughly 10 years. When the final black hole evaporates, the universe loses its last reservoir of mass. All that remains is radiation, photons, gravitational waves, and perhaps a few ultralight particles drifting apart in an ever-expanding space. Meanwhile, dark energy drives that expansion faster and faster. Measurements from NASA's WMAP and ESA's Planck mission confirm that expansion is accelerating. Over unimaginable timescales, distances stretch beyond limit, temperature differences fade, and interactions become impossible. Physicist Sean Carroll once wrote, "When there is no free energy, time stops being distinguishable." Events still exist, but nothing happens to mark time's passage. This smooth, cold future is exactly the condition CCC needs. Conformal geometry cares only about angles, not distances. Mass must vanish for distances to lose meaning. Once mass is gone, curvature dissolves. Horizons evaporate. The universe becomes scale-free. In that condition, the the universe's infinite future can be compressed mathematically into a single boundary surface that resembles the state of the Big Bang. Penrose says, "The remote future of our universe can be conformally equivalent to the Big Bang. This isn't poetry. It emerges from decades of mathematical work. Massless fields like photons and gravitational waves behave naturally within conformal geometry. NASA calls them scale-free messengers, revealing exactly why Penrose sees them as the bridge between one aeon and the next." In 2010, Penrose and Vahey-Gurzadyan proposed something even more extraordinary, that faint concentric circles in the cosmic microwave background might be remnants of black hole collisions from a previous universe. ESA's Planck mission later analyzed these claims. The evidence wasn't decisive, but it wasn't disproven either. This possibility lifted CCC from speculation into serious cosmological discussion. A previous universe might have left fingerprints inside our own sky. Behind this idea lies a century of scientific development, from the early work on conformal symmetry to Penrose's diagrams mapping black hole structure, to the Hawking-Penrose singularity theorems showing that spacetime must contain boundaries. CCC takes one more step. Those boundaries are not ends. They can be joined to and an aeon. The universe must satisfy precise conditions. No mass, no horizons, no temperature differences, no structures capable of defining scale when the universe becomes a bath of radiation with no meaningful curvature. Conformal geometry takes over. Distances become irrelevant. Infinity can shrink smoothly to a single surface, a surface that becomes the next. Big Bang.CCC doesn't require a cosmic explosion. It requires the universe to let go, to release mass, curvature, and thermodynamic gradients. And the remarkable part is that modern physics already describes every ingredient of this transition. Hawking radiation is supported through analog experiments and black hole thermodynamics. Proton decay remains possible. Dark energy is measured with increasing precision. All of these processes push the universe toward uniformity, toward stillness, toward the state Penrose calls the closing breath of an aeon. The moment one universe ends and another begins, the universe moves slowly toward a state where conformal symmetry becomes possible, a state where distances lose meaning and only angles remain. As the cosmos ages, every structure collapses, dissolves, or evaporates. Geometry, once sculpted by mass, gradually shifts into a form defined not by size, but by shape. And at that final transition lies the boundary Penrose calls the end of an aeon. But this boundary introduces a deeper scientific challenge, one no equation fully resolves. If an aeon ends as a universe filled only with radiation, perfectly smooth and devoid of scale, then what creates the first irregularities that seed the galaxies of the next cycle? Penrose offers one answer. Inflationary cosmologists offer another. And observational data continues to accumulate, pushing the question forward. Still, the mystery remains. How does a featureless conformal boundary give birth to a universe rich with structure? For a moment, that unanswered piece lingers. Then a new line of thought quietly emerges. If the universe fades into perfect smoothness, something must nudge it back toward complexity, something capable of lighting the first spark of the next beginning, and so the question sharpens. Part 3. What could truly trigger the next Big Bang? In the farthest reaches of cosmic time, The universe becomes so empty, so stretched, and so stripped of mass that the rules we once used to describe it begin to fall away. It is in this silent frontier that conformal cyclic cosmology proposes. The next Big Bang is born. The idea is extraordinary. A new universe ignites not from collapse or explosion, but because the old one becomes too smooth to distinguish size. Yet this idea is grounded in mathematics, observations, and the behavior of massless fields that NASA and ESA have studied for decades. To understand the true trigger of a new Big Bang, we follow the final steps of an aeon as it approaches its aeon, as it approaches its conformal boundary. In CCC, nothing detonates, nothing erupts. Instead, the universe undergoes a geometric shift so profound that an ending reshapes itself into a beginning, not metaphorically, but mathematically. The trigger starts with the disappearance of mass. Mass anchors the essential features of spacetime: horizons, curvature, gravitational wells, even the meaningful flow of time. When mass vanishes, the mathematical object that defines distances becomes flexible, free to stretch or collapse. Without altering the underlying geometry, Penrose summarized this with a single insight. In a massless universe, scale becomes meaningless. Without scale, the infinite expanse of the old universe can be compressed into something that mirrors the tiny, dense surface of a new beginning. This is not speculation. It arises from the behavior of massless particles like photons and gravitational waves. They have no rest mass. They carry no intrinsic scale. Their world lines can stretch across eternity and still be transformed smoothly into the boundary of a new universe. NASA often calls them scale-free messengers, because their motion depends on geometry alone. But scale-free geometry by itself does not create a new Big Bang. Something deeper must happen, a transformation in the causal structure of spacetime. When spacetime becomes conformally smooth, structure vanishes, temperature differences fade, curvature dissolves, horizons flatten out. The universe becomes a nearly perfect sea of radiation, drifting freely without producing new information. This is where CCC places the ingredients of the next beginning, not as a fireball, but as a geometric re-identification, a mapping where the final boundary of one aeon becomes the first surface of the next. The mathematics behind this took decades to build. Penrose's conformal diagrams, introduced in the 1960s, showed that the entire history of black holes, stars, and universes could be projected onto finite surfaces where infinity becomes manageable. His singularity theorems, developed with Stephen Hawking, revealed that spacetime inevitably reaches boundaries where classical physics cannot continue. CCC takes those boundaries and treats them not as ends, but as gateways, surfaces that can be reshaped when masslessness removes scale. Is this trigger physical or geometric? CCC suggests it is both. Geometrically, the end of an aeon becomes conformally equivalent to a Big Bang. Physically, the transition requires the disappearance of mass, of horizons, of temperature gradients, and of any structure capable of defining scale. Once these conditions are met, spacetime becomes so uniform that its infinite spread can be rescaled into the opening surface of a new universe. This rescaling is not optional. It is demanded by conformal mathematics, which ignores distance when mass no longer exists. But there is another ingredient: the vanishing of information. When all processes stop generating complexity, when every particle drifts too far to interact, when no new gradients form, the universe approaches a state where information no longer increases. This extreme smoothness is what allows the boundary of one aeon to be matched seamlessly to the birth of the next. If any irregularity remained, if wrinkles, gradients, or remnants of curvature persisted, the boundary would not align with the symmetry required to seed a Big Bang. Penrose once wrote, "The success of CCC depends on the universe losing every vestige of scale and structure. Only then can geometry become timeless, ready to fold into a new configuration." The hints supporting this mechanism come partly from observation. In 2010, Penrose and Vahey-Gurzadyan reported concentric Levariant circles in the cosmic microwave. Background possible signatures of black hole collisions from a previous aeon. Their claim generated intense debate. ESA's Planck mission reanalyzed the data. The results did not confirm the effect, but they also did not rule out models with conformal structure, leaving CCC within the realm of measurable cosmology. 2. Visualize how a Big Bang can be triggered. Imagine the final moments of the old universe, not in human time, but in pure geometry. First, every massive particle decays. Then, every black hole evaporates. Curvature softens. Temperature gradients flatten. Distances lows. Relevance. The universe becomes a sheet of scale-free geometry filled with radiation. This sheet becomes the conformal boundary when interpreted through the geometry of the next aeon. That boundary becomes the Big Bang surface, smooth, scale-free, and poised to blossom into a new cosmos. This raises one last question. Is the new Big Bang spontaneous or guided? CCC leans toward guidance. The fading patterns of massless radiation in the old universe imprint subtle global features onto the next. Photons do not age. Gravitational waves persist indefinitely. NASA's LIGO team once described gravitational waves as the purest messengers in the cosmos. These scale-free fields can cross the conformal boundary not as detailed maps, but as broad, gentle patterns that shape the earliest ripples of the next universe. The history behind these discoveries is filled with surprises. Hawking's black hole evaporation was once rejected, now foundational. Nordstrom's early work on conformal structures was nearly forgotten, now central to CCC. An ESA's Planck satellite revealed a universe smoother than expected, encouraging models, including CCC, where smoothness plays a defining role. All this leads to one striking conclusion. The trigger for the next Big Bang is not an explosion, but a transformation in geometry. When scale disappears, the universe sheds its identity as a physical space filled with objects, and becomes a surface defined only by angle, infinitely thin, infinitely extended, and ready to unfold into a new cosmos. Penrose captured this transition with unusual clarity. The boundary between eons is a conformal bridge. You arrive at a quiet threshold in the story of the cosmos, a place where one universe finishes exhaling, and another draws its very first breath. Here, at this delicate bridge, everything becomes weightless, and something ancient begins to reveal itself. Mass fades, scale dissolves, and in that silence, the old universe gathers itself into a final shimmering thread, a thread so compressed, so finely distilled, that it becomes the seed of a new beginning. But as you rest in this gentle idea, another layer, with the picture slowly forms around you a softer, stranger outline at the edge of Penrose's Conformal Cyclic Cosmology. If the next cosmos truly rises from pure geometry, then the boundary between eras must hold the tools that let orientation. Quantum spin and complex patterns survive the passage between worlds. Subtle structures that let one universe lean forward and whisper into the next. Part 4. Why spin? Complex numbers. And the Riemann sphere appear at the edge of two universes. There is a moment at the boundary of an aeon when geometry alone is no longer enough. Something more delicate is needed. Something that carries information without needing mass or time or scale. Here, the universe writes its final traces not in distance or motion, but in the language of spin, complex structure, and the strange, beautiful mathematics of the Riemann sphere. These ideas have followed Penrose for more than half a century. Not as decoration, not as mathematical ornamentation, but as the essential vocabulary for describing what might slip across the threshold, from one cosmos into the next. Spin, the quiet, intrinsic twist inside every particle, has always hinted at a deeper story. Long before modern physics matured, scientists noticed that electrons behaved as though they carried an internal, impossible rotation. The Stern-Gerlach experiment showed this in a single clean gesture. A beam of atoms divided into two paths, split by a property that could not be explained by any classical spinning object. Wolfgang Pauli later gave this behavior a new mathematical home, a two-component object requiring complex numbers. The spinner, from early in his career, Penrose, saw something profound in these spinners. He believed they were not merely tools for describing quantum particles, but the deeper architecture beneath space and time itself. Space and time are secondary, he once said. The spinner is fundamental, a bold statement, yet supported by decades of work showing that rotations, vectors, even light rays become simpler and more natural. When written in the language of complex numbers, spinners behave unlike anything classical. Rotate a spin 1/2 particle once, and its description flips sign. Only after a 720-degree turn does it return to the form you started with. Nothing in ordinary geometry does this. But the boundary between eons is not ordinary geometry. It is a place where mass evaporates, where size holds no meaning, and where only light-like structures survive. This is where the Riemann sphere enters. The Riemann sphere maps every complex number, even infinity, onto the surface of a single sphere. In Penrose's twistor theory, the paths of light rays in spacetime correspond almost magically to curves, and points on this sphere strip spacetime of mass, leave only the paths of photons and possibly neutrinos. And what remains looks astonishingly like the geometry of this very sphere in CCC. The final whisper of one universe is made only of massless particles, the ones that do not age, do not slow, do not decay. Their paths, their directions, their polarization, all can be written cleanly as spinner structures that map onto the Riemann sphere. So the universe's final radiation, its last, faint message, may be expressed in this delicate mathematical language. A powerful example comes from gravitational waves. When they were first detected in 2015, NASA described them as ripples in space-time carrying spin to information unchanged across billions of years. Their form is naturally written using complex mathematics, a hint that the universe's most persistent messengers speak the same language CCC uses at its boundary. Why does this matter for a new universe's birth? Because massless fields do not feel time. They stretch, but do not fade. Their direction remains meaningful. Their orientation stays intact. Spin, encoded in spinor form, may be the only physical quantity capable of crossing from one aeon to the next. This becomes even more compelling when considering conformal transformations. When scale disappears, angles remain, and spinors, which store direction rather than size, remain meaningful even when every distance in the universe shrinks to zero. This is exactly what CCC requires. Penrose and Gurzadine even argued that faint circular imprints in the cosmic microwave background may be echoes of black hole collisions from a previous eon. Gigantic spin-to events, whose patterns might survive the crossing and reappear in our own universe's earliest light. Debated, yes, but deeply suggestive. Twister theory itself weaves these ideas together. Each point in space-time corresponds to a sphere of possible light rays. Each light ray corresponds to a point on the Riemann sphere. Spin, light, and complex geometry merge into a single mathematical picture at the end of time, when the universe becomes a sea of massless radiation. What remains meaningful is not size, but direction. Not position, but relation. Not distance, but angle. Spinors capture exactly these things, and so they become the natural carriers of whatever faint information one universe may pass to the next. Even the quantum behavior of spin supports this. Spin determines how particles respond to symmetries and rotations, how fields transform, how interactions unfold. NASA describes spin not as physical rotation, but as a quantum rule governing how the universe behaves at the deepest level. If anything crosses the boundary, spin-based correlations are strong candidates. But does spin truly survive the crossing? CCC suggests that it does not as particles, but as patterns in massless fields that remain smooth when scale collapses to nothing. The universe forgets mass, it forgets distance, but it may not forget direction. Dirac, in the 1930s, saw beauty hidden inside spinor mathematics. His equations predicted antimatter, one of physics' greatest discoveries. Penrose later extended this heritage, showing that twistors unify light rays, spin, and complex geometry into a single language that remains valid even when itself loses its traditional meaning. The Riemann sphere, in this light, becomes a cosmic canvas, a surface where the final radiation of an aeon is gathered into a finite structure that can be handed to the next universe. It answers a quiet question. Does quantum information survive the Big Bang? Not as particles, but as geometric patterns etched into the conformal boundary. Part 5, is space-time truly cyclical in CCC? Eventually, the story reaches an unavoidable question. If one universe ends and another begins, does space-time itself move in cycles? Or do eons unfold like pages in a book that never loops back? Penrose's answer is gentle and subtle. He does not claim a perfect cosmic loop. Instead, he imagines a chain of eons, each one with its own beginning, its own long expansion, its own smoothing into a scale-free, massless ocean. Time does not rewind. It does not fold onto itself. Each eon becomes the foundation for the next. To see why, you follow the logic of general relativity. Einstein showed that time is not fixed. It bends with gravity, stretches with motion, responds to energy. NASA once explained that time behaves like a dimension shaped by the curvature of spani, far in the universe's future. As mass decays, as black holes evaporate, as curvature flattens, time loses the markers that give it rhythm. No orbits, no gravitational structure, no thermodynamic gradients. Time still exists, mathematically, but its physical meaning dissolves. And that dissolution is exactly what allows the boundary between eons to act not as an ending, but as a bridge, a smooth, scale-free surface where one universe hands its final geometry to the next. In this gentle vision of the cosmos, nothing loops back, but nothing is ever truly lost. Each eon rises from the softened light of the one before, a quiet, unending sequence of beginnings woven from endings.
These discoveries formed a single, elegant narrative. Our universe has a clear beginning, but CCC adds a deeper layer, one suggesting that the end of a previous eon may have quietly supplied the initial conditions for our own beginning. This does not imply a traditional cycle. A classical cycle repeats itself. CCC does not. Instead, it replaces repetition with conformity, a mathematical process where the infinite expanse of one universe is reshaped into the initial surface of the next. This brings us to the next question. Does space recycle itself? Or is every eon born with entirely new structure? In CCC, space does not loop back or restore old geometry. It transforms. As the old universe expands, its matter decays, black holes evaporate, and mass asymptotically approaches zero. With mass gone, distances lose meaning. Scale becomes irrelevant. What remains is pure conformal structure, geometry expressed not through lengths, but through angles and relationships. This is what allows the unimaginable immensity of a dying cosmos, billions of light years across, to be rescaled into the newborn geometry of the next Big Bang without contradiction. Penrose often describes it simply. In the absence of mass, infinity and zero become interchangeable. It sounds abstract until we consider how massless particles behave. Photons experience no time. Gravitational waves carry information across billions of years without losing their angular imprint. Both are naturally described by conformal geometry. This is why CCC treats them as the only physical quantities capable of linking one eon to the next. But then another subtle question arises. Does the orientation of fields survive that crossing? Does the shape of space itself leave a faint echo? NASA's gravitational wave teams have noted that gravitational waves maintain their angular information across extraordinary distances. They called them the purest long-distance signals ever detected. If such waves stay coherent over billions of light years, then under conformal smoothing, their angular patterns might imprint the next universe, not as physical waves, but as geometric predispositions. This leads us to an even deeper inquiry. Do eons influence each other? Penrose's answer, not through particles, but through geometry. The conformal boundary of one eon becomes the starting surface of the next, an inheritance of shape, stripped of scale. It is not recycling, it is transformation. Here, the Riemann sphere and twistor geometry from Part 4 quietly re-enter the picture. Twistors encode light-like structures using complex numbers and directional geometry. Because twistor space is naturally conformal, It provides a mathematical language capable of describing whatever faint information survives the massless end state of an aeon. In this view, space-time becomes less a grid and more a web of angles and relations, a whisper of structure preparing the conditions for a universe yet to be born. This brings us back to time itself. Is time cyclic? In CCC, every aeon has its own internal timeline, beginning with its Big Bang and stretching toward a future where mass fades away. These times are not shared. They do not merge. They do not rewind. Time begins again with every aeon. CCC treats the transition not as a loop, but as a geometric identification, an elegant stitching together of two eras that no longer share a common sense of scale. This idea resonates with a long tradition of questioning the nature of time. Carl Sagan once said, "We are a way for the universe to know itself." CCC echoes this sentiment, but grounds it in physics rather than metaphor. Every aeon is a new instance of cosmic unfolding, shaped but not determined by the aeon before it. Observations strengthen this idea. The cosmic microwave background, the CMB, mapped by NASA's WMAP and ESA's Planck mission, is astonishingly smooth. Inflation was proposed to explain this smoothness. But CCC offers another possibility. The uniformity may be inherited from the previous aeon's massless, conformally smooth geometry. The tiny fluctuations we observe today, especially those JWST detects in the deep infrared, may reflect quantum irregularities seated at the Big Bang, possibly influenced by faint geometric traces from earlier eons. Historically, the idea of conformal spacetime has deep roots. In the 1950s, mathematician Hermann Weyl explored conformal symmetry and suggested that certain laws of nature remain unchanged under rescaling. Penrose later expanded these ideas, showing that mass is the only barrier preventing spacetime from adopting conformal behavior naturally. Remove mass, and the universe becomes conformal by default. This leads to a key understanding. CCC does not claim the universe loops. It claims the universe transitions. Each aeon is connected not by repetition, but by geometry. Imagine a vast sheet stretched endlessly. Now imagine shrinking that sheet into a sphere without distorting any of its angles. Conformal mapping makes this possible. CCC applies this transformation to the universe. So is space cyclic? Not in the classical sense. Its conformal structure survives. Its scale does not. Space is reborn not as a copy, but as a new manifold, shaped by the final geometry of the preceding aeon. Is time cyclic? No. Each aeon contains its own self-contained timeline. Do Big Bangs link mathematically? Yes, through conformal smoothing, twistor structure, and the geometry of light. These elements allow one aeon's end to align seamlessly with another's beginning. And from within this picture, a quieter and more delicate question emerges at the edge of thought, one sitting at the heart of CCC's vision. If time resets with every aeon, then where does life fit within the lifespan of the universe? Does life matter cosmologically? Does it play any role at all? This leads us into part 6. Does life influence the evolution or lifespan of the universe itself? Life reaches its quiet conclusion when the gradients that once fed it gently fade away, when stars dim, when worlds cool into silence, when black holes finish their long evaporation. The universe enters a stage where no structure remains capable of creating new patterns. This is not death in any biological sense. It is a soft closing of a thermodynamic story. The moment the cosmos can no longer generate novelty is the same moment it begins preparing for the conformal transition you explored earlier. What makes this connection profound is that both life and cosmology unfold through the language of entropy. Life shapes small pockets of order while increasing disorder around it. A universe that can host life is one filled with winds of energy, gravity carving pathways, heat flowing across matter, stars fusing elements into light. A universe that cannot host life is one where entropy has nearly settled, where every gradient has flattened into stillness. Life, then, is not the goal of an aeon, nor its endpoint. It is a brief expression of the universe's ability to weave structure from contrast, a symptom of cosmic richness, not its definition. Yet this realization guides you to a deeper wondering. Does the appearance of life signal a turning point between chaos and form? Or is it simply one luminous chapter in a much larger thermodynamic evolution? When you look at data from ESA's Gaia mission, you see billions of stars forming, shining, cooling, and dissolving according to laws written in gravity and nuclear physics. Life arises in the middle of these cycles, shaped by them, dependent on them, and it vanishes when those cycles end. From this view, the story of life becomes the story of energy itself. This perspective helps us approach another quiet question. Does life continue into the next eon? Under CCC, life cannot pass through the conformal boundary. The crossing erases mass, and without mass, biological structure has no meaning. But the role life plays, processing information, shaping complexity, may leave a subtle influence on the geometry of its eon. Not direct, not personal, but faint echoes that might blend into the patterns the next universe inherits. And here, a delicate realization forms. A place where life, entropy, and cosmology seem to lean toward the same mysterious edge. If life is only one way the universe arranges information into form, then what becomes of that information as an eon thins out and drifts toward the conformal horizon? This leads to the next thought. Part 7. Does quantum entanglement survive the end of a universe? It is a question even seasoned physicists speak of with hesitation. If the cosmos becomes perfectly smooth at the end of an eon, does entanglement, nature's deepest connection, vanish? Or might it linger within the last radiation that slips across the conformal boundary? To explore this, you return to what entanglement truly represents. In the early 20th century, Einstein, Podolsky, and Rosen described a scenario where two particles behave as a single system no matter how far they travel apart. Einstein called it spooky, a word that still appears in modern discussions at NASA. Entanglement is not a signal, it is a correlation, a relationship that cannot be explained through classical thinking. And these correlations can endure across astonishing distances. JWST has captured light from galaxies whose photons began their journey more than 13 billion years ago. If those photons were entangled when they formed, the connection could still be measurable today. This extraordinary resilience leads to an unexpected possibility. Could entanglement survive the entire lifespan of an eon? To approach this, you look at how entanglement behaves in our present universe. It can form through countless processes, particles interacting, photons splitting, atoms shifting states. Experiments at NIST have demonstrated entanglement between ions separated by several meters. Proposals like the Space Quest mission. Every test shows the same truth. Entanglement only fades when disturbed by its surroundings, through a process called decoherence. But what happens when the surroundings vanish? As the universe ages, interactions slow. Stars fade. Black holes release their final radiation. Protons may decay. Temperature differences disappear. Structure dissolves. The emptier the cosmos becomes, the fewer ways decoherence can occur. And so, surprisingly, a dying universe may protect entanglement rather than erase it. Consider the cosmic microwave background. Light that has traveled nearly unchanged for 13.8 billion years. If entanglement had been present in its early state, nothing would have existed dense enough to erase it. In this sense, entanglement is fragile in crowded places, but almost eternal in empty ones. In the far future, when massless particles dominate, decoherence becomes rare. The environment becomes too thin to disrupt quantum correlations, which means the last threads binding particles and fields may outlast stars, galaxies, even matter itself. But what about the moment CCC relies on, when mass disappears. Massless particles follow paths untouched by time. Photons do not age. Their quantum states remain steady. At the conformal boundary, interactions are so weak that entanglement could become one of the final surviving features of the universe. This idea gains support when you remember how entanglement behaves around black holes. Hawking's work on the information paradox sparked decades of debate. The modern viewpoint is subtle. Information is not destroyed. It is encoded in correlations. If entanglement can persist in the intense environment near a black hole's horizon, it may also persist in the quiet, nearly interaction-free future of a dying aeon. But does it cross into the next universe? To answer this, you return to the heart of CCC. When mass vanishes, the universe becomes scale-free. Distances stretch into meaninglessness. Only angles remain. Only light-like paths carry structure. Penrose's mathematics shows that these null paths map smoothly onto the early geometry of the next Big Bang. Spinorial and twistor structures may preserve directional relationships. If entanglement is encoded in phase and angular correlations, then these patterns might pass through the transition, not as particles but as relationships. This implies something bold. The last light of a dying aeon may carry entanglement that seeds the earliest quantum fields of the next. History reminds us that unexpected remnants can survive cosmic transitions. When Penzias and Wilson discovered the cosmic microwave background, they were listening for noise. Instead, they found ancient photons carrying information older than any star. If thermal photons can preserve structure for billions of years, then the massless radiation at an aeon's end might preserve quantum correlations far longer. The question then deepens. If entanglement persists, does it influence the next aeon? CCC suggests it might, subtly, softly, invisibly, through faint biases in the earliest fluctuations of the newborn universe. These would not be memories. They would be whispers of geometry. This leads to a remarkable insight. Entanglement may be the universe's final thread, the last distinction before scale dissolves, and possibly the only quantum feature capable of bridging one aeon to another. As this idea settles, another question rises gently from the horizon of thought. If entanglement can survive the end of an aeon, what becomes of information itself as the universe crosses into the next? Part 8. Does information survive the boundary between aeons? Here lies one of physics' hardest questions. When an aeon reaches its quiet end and transitions into the next, does information accompany it? Or does the new cosmos begin with a perfectly clean slate? To explore this, you first understand what physicists mean by information. It is not metaphor. It is the arrangement of energy and fields, the measurable distinctions that determine how a system can evolve. Information is woven into atoms, photons, quantum fields, gravitational ripples, and the very shape of space-time. So when you ask whether information survives across eons, you are asking whether any of these structural differences can remain meaningful when the universe becomes massless, scale-free, and conformally smooth. This question links directly to the black hole information problem. Hawking once suggested information might vanish in black holes. Later, he revised this view, proposing that information may be encoded in correlations within Hawking radiation. LIGO's observations of black hole mergers supported this idea. Their gravitational waves carried extraordinary detail across more than 1 billion light-years. If information can survive environments that extreme, you naturally wonder, could the final radiation of a dying aeon also preserve faint traces of its history? As the universe nears the conformal boundary, mass fades, interactions soften, and only massless radiation remains. Photons, gravitational waves, perhaps ultralight neutrinos. This radiation is almost uniform, but not entirely featureless. Information can hide in angular correlations, not in distances. And conformal transformations erase scale, but preserve angles. Which means that any information encoded in these angular relationships may pass into the next universe. To see why this matters, you return once more to the cosmic microwave background. ESA's Planck mission mapped tiny temperature variations with exquisite precision, fluctuations that trace back to the earliest moments of the cosmos. If such delicate structure can survive almost 14 billion years, it is natural to wonder whether similar patterns might also survive the soft, smooth ending of an eon. Quantum mechanics adds another piece. Fundamental laws say information cannot be destroyed. Decoherence hides it, but does not erase it. Even black hole radiation, once thought to lose information, is now understood to encode it subtly. NASA summarized this shift clearly. Black holes do not destroy information, they redistribute it. This alignment between black hole physics and CCC is striking. Both suggest that information might survive even when mass and structure dissolve. You settle into stillness, letting your breath soften as the universe quietly opens before you. Here, in this slow and gentle moment, you drift toward questions older than stars. Questions about what remains when one cosmos ends and another begins. To understand what might survive such an unimaginable transition, you turn your attention to one of the most discussed ideas within conformal cyclic cosmology, the mysterious, faintly drawn circles in the cosmic microwave background. Penrose and Gerzadian once suggested that these circles could be gentle echoes from a universe that lived before ours, ripples shaped by bursts of gravitational waves long before this eon began. Whether or not those patterns are real, the idea behind them matters. That information may cross the boundary between eons not as particles or matter, but as smooth, angle-based patterns carried by fields that no longer possess mass. And yet, you consider the opposite possibility. What if the boundary wipes everything clean? What if the universe stretches so far and becomes so uniform that all distinctions dissolve, entropy climbing toward its final peak until every gradient fades away? A vast sea of radiation, a cosmos without memory. But even in that smoothness, something subtle resists erasure. Quantum mechanics leaves behind its faint fingerprints. The vacuum is never truly empty. Tiny fluctuations still dance in the quiet. Experiments like the Casimir effect and observations of vacuum polarization reveal that even at the lowest energies, fields hold correlations, threads of structure that refuse to be undone. If those threads cannot vanish entirely, then information cannot vanish either. It can be stretched, diluted, softened beyond recognition, but never fully erased. And this leads you to a quiet, delicate question. Does a newborn universe inherit the smallest trace of structure from the one that came before it? Just enough to guide its earliest fluctuations, yet not enough to disturb the gentle smoothness required for a new beginning? Penrose once imagined that information might cross the boundary not as content, but as constraint. Not the events of the old universe, but the way its geometry was shaped at the end. The history of this idea is long and winding. In the 1970s, Hawking's early proposal of information loss in black holes was widely accepted. By the 1990s, new ideas from string theory and holography began to challenge it. In the 2000s, the ADS/CFT correspondence suggested that information could be written on boundaries rather than destroyed inside horizons, an echo of CCC's own boundary between eons. By 2019, NASA summarized this shift simply. Information conservation appears to be a fundamental rule, even in spacetimes with horizons. Together, these concepts, black hole horizons, holographic surfaces, conformal mappings, paint a picture where information may be far more durable than we once imagined. CCC makes a precise claim. The transition between eons preserves conformal structure exactly. Anything based on angles, phases, or patterns of correlation can pass forward. Anything that depends on scale, atoms, molecules, biological forms cannot. Nothing is fully saved. Nothing is fully lost. Only the parts compatible with massless, scale-free geometry remain. To picture this, you imagine projecting a detailed painting onto a sphere, then gently removing every color and shadow until only its outlines remain. The picture is no longer recognizable, but it isn't gone. Only its simplest contours survive. CCC suggests that the universe performs the same act at the end of an aeon. The next Big Bang inherits not the story of the old universe, but the boundaries that shaped that story. Directions without distances, phases without amplitudes, just enough to see the first quantum ripples while keeping the newborn cosmos smooth. This brings you to the central question of this chapter. Does CCC violate the principle of information conservation? Not quite. It reframes it. Information tied to mass cannot pass through. Information expressible in pure geometry can. In this way, CCC stays aligned with quantum mechanics, black hole physics, and modern cosmology. But now another question rises quietly, more delicate and more intimate. If only conformal information survives across eons, how long does the universe maintain the kind of usable energy that life itself needs to create information at all? To explore this, you turn toward the nature of biological energy. Life, in its simplest scientific description, is a system that turns free energy into structure. NASA's astrobiology program puts it simply. Living systems survive by feeding on gradients, differences in temperature or chemical potential that allow energy to flow and power metabolism, movement, replication, and information. Nearly all life on Earth traces its energy back to the sun, pouring out roughly 3.8 times 10 superscript 2 watts of radiant power. Plants capture a small fraction of that light, storing it in chemical form. Animals use that stored energy. Cells survive only by maintaining differences, tiny gradients of ions and charges that keep life in balance. In the 1950s, biophysicist Schrödinger described life as a system that feeds on negative entropy, meaning it uses environmental order before disorder spreads. Modern thermodynamics explains this gently. Life does not defy entropy. It simply runs on the temporary availability of free energy. From a cosmic perspective, this explains something profound. Life continues only as long as the universe still offers gradients strong enough to support it. As long as stars burn, planets cool, oceans flow, and atmospheres circulate, biological processes can thrive. But none of these gradients last forever. Stars exhaust their fuel. Planets lose heat. Galaxies grow dim. As the universe expands, energy becomes more diffuse. The great cosmic gradients flatten. To understand this decline, you look back across cosmic history. In the early universe, gradients were enormous. Matter clumped under gravity, igniting the first stars. JWST's deep images reveal galaxies shining only a few hundred million years after the Big Bang, their radiation shaping the chemistry that life would eventually depend on. Life emerges only when the universe becomes cool enough for molecules to survive, but warm enough for energy to flow. Earth entered that window about 4 billion years ago, and everything living follows from that thermodynamic opportunity. But the window is temporary. As stars burn out, fusion slows. Massive stars collapse or explode. Stars like our sun swell into red giants. White dwarfs cool across trillions of years. Black holes evaporate over timescales beyond imagination. All of this pushes the universe toward equilibrium, toward a time when gradients vanish and entropy peaks. When that happens, biology can no longer be sustained. This pattern is not speculation. It's the direct consequence of thermodynamics. Life does not end because of cosmic catastrophe. It ends because the gradients it depends on fade into stillness. Information, too, depends on energy. Every mutation, every neural pattern, every ecological shift is written using free energy. When energy becomes scarce, the creation of information slows and eventually halts. Cosmic history cannot be separated from thermodynamic history. Life begins when gradients rise. Life ends when gradients fade. And this brings you back to CCC. Does the disappearance of biological energy signal the end of an aeon? Not exactly. Life ends when free energy becomes too thin to support complexity. The universe continues long past that point, gradually smoothing into a sea of massless radiation, the state required for the next conformal transition. The end of life is not the end of the universe. It is simply the point at which complexity can no longer be sustained. Black hole thermodynamics offers a striking parallel. As a black hole evaporates, it loses energy, heats up, and ends in a final burst, after which only radiation remains. Hawking described this as the evaporation of order. The universe undergoes a similar slow smoothing. Free energy becomes structure, then heat, then almost featureless radiation. Life uses the early stages. Gravity shapes the middle stages. The late universe moves towards stillness. And now, in this quiet reflection, you see what biological energy reveals. Life occupies only a brief window in the lifespan of an eon. Astrophysical data show that star formation peaked around 10 billion years ago and has been falling ever since. Long before an eon reaches its conformal end, the energy needed for life fades. Life disappears not when the universe ends, but when gradients fall too low for complexity to persist. Biological energy becomes a kind of cosmic clock, not measuring time by expansion, but by the universe's ability to support structure. And in that understanding, you rest, drifting gently into the soft, spacious quiet where questions expand like starlight and the universe breathes in long, slow cycles across unimaginable ages. When we view the cosmos this way, life is no longer something separate from astronomy or physics. It becomes a temporary phase in the universe's long thermodynamic journey. Its birth marks the rise of gradients. Its fading marks the thinning of structure. And its absence quietly foreshadows the massless, conformal future described by CCC. As this understanding settles like a soft cosmic dusk, a new question begins forming, slowly, gently, at the edge of thought. A question not about stars or biology, but about consciousness and the geometry of space-time itself. If the universe advances through eons shaped by geometry, masslessness, and information flow, then what do ideas like panentheism, panpsychism, and the nature of space-time mean beneath the lens of modern cosmology? Part 10. How do panentheism, panpsychism, and space-time fit into conformal cyclic cosmology? There comes a point when scientific questions become so sharp that they pierce straight through concepts usually considered philosophical. If space-time stretches across multiple eons, if information can travel through conformal boundaries, and if consciousness arises from physical processes tied to energy and structure, then these questions transform from speculation into scientific challenges. To explore this properly, we begin where CCC begins, with space-time itself. Einstein's field equations link mass energy with curvature, forming a living fabric that bends light, shapes galaxies, and carries gravitational waves. NASA often describes this relationship simply. Space-time tells matter how to move. Matter tells space-time how to curve. This dynamic works flawlessly within each eon. But CCC proposes something far more daring. When mass disappears at the end of an eon, space-time becomes conformal. Its scales fade away, but its angles remain. And in that moment, stripped of mass, its geometry can map directly onto the next Big Bang. This means space-time itself becomes the bridge between universes, not as a substance, but as a continuity of pure geometry. This idea has deep mathematical roots. In the 1920s, mathematicians studying Riemannian geometry discovered that certain structures remain unchanged even when distances are stretched infinitely. In the 1950s, mathematician Hermann Weyl noted that electromagnetic fields retain their structure under conformal transformations. Penrose unified these ideas through twistor theory, showing that massless, light-like structures behave beautifully when scale is removed. Under CCC, this becomes the central principle. The universe does not carry its matter into the next cycle, but it may carry its geometry. Panentheism, reinterpreted through geometry, Panentheism is often misunderstood as a spiritual concept, but scientifically it raises a precise question. Is our universe part of a larger mathematical structure? CCC supports this, not metaphysically, but geometrically. Each aeon is not isolated. It is one chapter in a vast lineage of cosmic cycles, each obeying the same conformal rules. From this view, the universe is a phase inside a greater pattern, a sequence of aeons woven together by geometry, not by matter. Panentheism, reframed scientifically, becomes a statement about embedded geometry, not divinity. Panpsychism, consciousness through the lens of physics. Panpsychism suggests consciousness may arise from fundamental aspects of matter or space-time. CCC does not endorse this idea, but it forces us to examine it under physics. If consciousness is a type of information processing, then its existence depends on energy gradients, as we explore in Part 9. However, modern physics recognizes something important. Information is woven into the structure of fields themselves. NASA's quantum information research notes that information can be stored in field correlations independent of the particles carrying them. This means not that consciousness exists everywhere, but that the structures enabling consciousness re-emerge from the deep patterns of space-time. CCC suggests that while consciousness does not survive into the next aeon, the structural canvas that allows consciousness to form does. Each aeon resets the geometry to a smooth beginning. Stars ignite, gradients emerge, complexity rises, and once again, consciousness becomes possible, not through memory, but through recurrence of physical conditions. Space-time, the engine behind the cycles. In CCC, space-time is the silent architect of cosmic rebirth. It is space-time that preserves angles when all scales dissolve, carries light-like directions across eons, transmits subtle correlations through conformal boundaries, and provides the smoothness observed in early universe measurements. Inflation explains this smoothness as rapid early expansion. CCC proposes a simpler origin. The smoothness was inherited, passed gently from the previous aeon through the conformal boundary. Gravitational waves strengthen this idea. LIGO's first detection showed that space-time can carry incredibly detailed information across billions of light-years without distortion. If such waves endure an entire aeon, their angular patterns might also survive the conformal transition. So what do these ideas mean together? Panentheism becomes a geometric question. Are eons part of a larger mathematical structure? Panpsychism becomes a physics question. Does space-time naturally generate the patterns from which consciousness emerges? Space-time becomes the engine of the cyclic universe, preserving angles, shaping fields, and carrying information forward. CCC does not claim that consciousness continues across eons, but it suggests that the cosmos naturally rebuilds the conditions that allow consciousness to arise. Each aeon resets the universe. Each aeon rebuilds gradients. Each aeon allows complexity to flourish once more. As we drift toward the end of this part, thank you for staying with me in this quiet place of ideas, where physics touches philosophy gently. If tonight's journey brought you a moment of peace or a new thought to rest upon, I'm grateful. A soft like or a tiny tap on subscribe is always a warm encouragement for me to continue these long night stories. And if you feel comfortable sharing, I'd love to know where you're listening from tonight. Those little messages feel like distant stars guiding me forward. Wishing you a deep, peaceful sleep. I'll meet you again in the next journey, somewhere among the silent galaxies of understanding.